Yesterday we solved for ice boxes, and all we did was we finished what the final concentration was. We are now going to go back to that same worksheet. We are going to write our equilibrium expression, and we are going to solve for K. In addition, we're going to learn about using icebox to solve for concentrations when we're given our equilibrium constant. So there are several things we're going to use ice boxes for. We've already solved for our equilibrium concentrations if we're given one equilibrium concentration. Now we're going to use those same ice boxes to solve for K. Now we're also going to solve for equilibrium concentrations when we are given K. We're going to do this with a perfect square. We're going to figure out when we can ignore our X values. And when we ignore our X values, we're only ignoring the subtraction or the addition, not the multiplication of the X. And then we are going to solve using the quadratic formula when we don't have a perfect square and we cannot ignore our X. So here's a problem solving for K using initial concentrations and final equilibrium concentrations. First, you always have to write your equilibrium expression, okay, because that's our formula. It doesn't matter what problem we're doing, you have to do that. And then we're going to use an icebox. So these numbers right here, 2x, x, and 2x come directly from our coefficients from our balanced equation because our icebox is basically set up using stoichiometry, and this is very similar to the BCA chart. Okay, so let's tackle this problem. Our initial is given from the problem. We have 1 atmosphere of NO, nitrous oxide, 1 atmosphere of oxygen, and that's put in initially, and initially there are no products formed. Okay, now I didn't use sig figs here because I want it to be clear so you can see what's going on, okay? Now what happens? Well, 2 times a certain pressure goes away from NO. Why? Because our coefficient is 2, so that's a 2x. Oxygen only 1 time goes away, and then we have 2 times as many products formed. So that's our change, minus 2x and x and plus 2x, okay? So then at equilibrium, what do we have? Well, we started out with 1 atmosphere of pressure and 2 of a certain amount left, right? Now, they gave us this concentration, 0.506 for our oxygen. And what you have to remember is that this is 1 minus x equals 0.506, okay? Do not get lulled into the fact that you think that's 0.506, because remember, we started with 1, and at equilibrium, it's 1 minus x, okay? And then 0, and we made 2x, so 2x is for nitrogen dioxide. Okay, so when we solve for x, x is 0.494. And now we can finish off our final concentrations. So when I put all that in and I plug in for x, I get my equilibrium concentrations for nitrous oxide 0.0012 and for nitrogen dioxide 0.988, and then I plug that into my equilibrium expression and I can solve for K, and my K is 1.34 times 10 to the 6th. So sometimes we are not given a final concentration. So I have to solve for concentrations, but we are given our equilibrium constant. So for here, the first thing you do is you solve for your equilibrium expression, and then you're going to write out your icebox. So I have my initials and my change is based on stoichiometry, minus x minus x minus 2x. And then at equilibrium, well, what did I start with? What's my change? I put that all together, and now I have these expressions for each of my reactants and products, and I am going to plug that into my equilibrium expression. Okay, so when I plug that into my equilibrium expression, and remember our K was 64, 64 is something I can take the square root of, and if you notice, if I take the square root of both sides, I come out with this. Why? Because it's a perfect square, right? This is 0.2 minus x squared. I have two of these guys here, okay? And then I can take the square root of both sides, rearrange, and solve for x, and I get x equals 0.16 molarity, okay? And then you can plug that in and you can solve for the equilibrium concentrations for every single species. Okay, now if our KEQ is really, really small in a reaction, what we can do is we can ignore this x. So notice this x right here would be 2 times 10 to the negative 1. If my equilibrium constant is 3 magnitudes different than that, and what does that mean? Magnitude is the power of 10. So if that's to the minus 1 and I have to the minus 4, I can ignore that x, because when I subtract that number, it's really just a negligible number. 0.2 minus 0.00002 still gives me 0.2 in significant figures. Okay, so if you cannot ignore x and we don't have a perfect square, you would have to do the quadratic formula. In this problem, we have two problems, A and B. One where I can ignore x, and one where I'm going to have to use the quadratic formula. So let's first of all look at our equilibrium constants here. And they're different because I have different temperatures for the same reaction. Okay, so what I notice right away right here, let me change my color, is I have an equilibrium constant that's to the minus 10. That means that my reaction lies far to the left. I am not going to make very many products, so any change that happens is going to be very, very, very tiny. Okay, so let's set up that problem. And I have my change, my ice chart that I'm going to set up. I'm going to plug it into my equilibrium expression, and then I need to decide, can I ignore this x right here? Now remember, you can ignore the minus x, not the multiplier. So what do I see here? I have more than 3 orders of magnitudes between the numbers. Which numbers? Well, we are talking about our K versus our concentration, right? This would be 2 times 10 to the negative 1 versus to the negative 10. I have more than 3 orders of my power there, so I can ignore that x. So there we go. And again, this is what I explained. We are subtracting such a small number that with significant figures, it's not going to change that number at all. So now I have a new expression without the minus x, and I can solve very simply, where x equals 3.83 times 10 to the negative 6, and I can plug that in and get my equilibrium concentrations. Okay. Now, here is one where we need to use the perfect, or we need to use a quadratic equation. Let's see why. So we are going to set up my ice chart. Okay, and then we are going to have our equilibrium expression, and we are going to plug it in. I do not have a perfect square, and as you can see, this is to the minus 3, and if we just take one of these concentrations, that's 2, 6 to the minus 2. So I cannot ignore that x. I am not past the 3 magnitude rule. So I'm going to solve this problem out so I can figure out my quadratic formula. Okay? So there it is, solved out, and you need to make it equal 0 so I can plug it into my quadratic formula. Remember, this is the generic form of this equation, so you know what your A's, your B's, and your C's are. I'm assuming you've all used that quadratic formula, yay. And so when I solve this, I get x as 2 different numbers, and you need to plug it in and decide which one is correct, okay? So if I plug one of those numbers in, I get a negative molarity. Now that can't work, so that can't be the correct one, okay? So if I plug the other one in, I get a positive molarity, and so that is the correct number of what my x is. Okay, so it can't be that guy. It has to be that guy. And then I can plug in my numbers and I will get